So yes, I'm with Agility Robotics, and it's been a long and recently nearly complete transition from being a professor at Oregon State University. This is a spin-out company, started in 2015, so we've been at it for a while here. And I thought I would start a little bit with what's our purpose and what's our goal. And I think our vision at Agility Robotics, we want to enable humans to be more human. And I think this is something that the entire robotics community gets behind and is trying to do. We're building better tools. Robots can do the dull, dirty, dangerous things that we don't want to do and allow humans to be more human. That's what we're trying to achieve. Now, in the near term, what are we doing today that's really valuable, that's really important? We're building robot partners to augment the human workforce. The whole point of this is to have robots that can operate in human spaces, in human environments, that can go where people go. It's interesting that where we've gotten here to this configuration and the shape of the robot is, I want to make this really clear, we're not trying to mimic a human in its form. We didn't set out to make a robot that looks like a person. We set out to build a robot that has a lot of the same performance features. And I'll talk a little bit about why that sort of pushed and shoved us into this direction from basic first principles. But it's also a company, and we want to be doing useful things in the world and have to be able to solve problems for customers. So we are going to be unloading tractor trailers. We're going to be moving totes around. The versatility and the value in it is in being able to do many different things.
Well, let us just remove the focus.
What's it about that?
Is it this?
Yeah. Now, eventually it'll mature to the point where you can have an app store for labor. It's not there yet. Right now, we are focused on solving that specific problem for our customers, unloading the tractor trailers. But okay, so I'll back up a little bit and I'll start on some of the technical things. Just kind of the hierarchy and a little bit of history. Oops. All right. So this is kind of, a while ago, and this is Digit walking around on the ground. The thing that's really interesting here is, it's a combination of the passive dynamics of the machine. You care a lot about the inertias of the limbs. You care a lot about physical springs or compliance. You care a lot about the friction through your device and the forces you're able to apply to the world. And what we're trying to do is build kind of this low-level foundation of things. It's absolutely not position control, right? The trajectories and where the foot do matter, but that's one of many things that matter a lot. And it's a very familiar feeling when you step off the edge of a curb and you miss it. And in the case of this bird and in the case of our robot, the foot just extends straight down to the ground because it's trying to apply some force and it's able to, the tissue paper, of course, won't support that way. And so it just extends that foot straight down into the ground. And so that kind of dynamic stability is a little bit, it's not decision making, it's engineering a set of dynamics in a system. And that's kind of that low level. And it's hard to imagine, how do you kind of connect that to the higher level planning and perception, which typically is about being somewhere, being in a position, following a trajectory. But that's been the foundation of the background. Is what can we first capture the physics of what we see animals and humans do, and can we capture that kind of behavior and robustness? I guess everybody is doing reduced order models. I think that's fundamental. I don't think that's just an engineering approach. I think that however you generate it, however you create it, some sort of reduced order model is kind of a necessity for how you're going to control the system or control robots in the world or how animals are controlled in the world. Lots of different tools to do it. So, again. I'm going to tell a little story on this slide. So this is the history, right? This is Thumper, which was quite a while ago. It's just a 2 degree of freedom robot that was on a boom. And the bipedal version of this was Mabel at the University of Michigan. Each stage here, there was a lot of learning. And there's a sort of thread, a train of thought into the development and configuration of the leg and the shape as it goes. So starting with Thumper, the whole idea was kinematically constrain it so that you have a pogo stick, so that you have one motor in leg length with a spring in series and one motor in leg length. And it worked quite well, but there's a fair bit of inertia. That's why it was called thumper. Every time you hit the ground, hopping around the lab, it's very loud. They put me in the basement, on the concrete floor, so it wasn't near other people. And kind of the recognition, the realization there was, we don't have to have it be kinematically constrained so that one motor is leg length, one motor is leg angle. You can coordinate your motors in every which way. You just want to get the dynamics right. And that's what Atreus was. Atreus was designed to be as close as possible to the reduced order model, to the spring mass model. Physically, can I create a spring mass model as close as possible? So those pantograph legs are a lot like the high-speed pick-and-place robots for the same reason, super low inertia. Big physical springs in series, and then all the motors, everything concentrated. So Atreus is an acronym. Assume the robot is a sphere. Try to make it as simple as possible, and you can just assume the robot is that reduced order model, and all are really basic heuristic controllers. You don't have to think about inverse kinematics or inverse dynamics or complexities of robot control. You just assume the robot is a string mass model. And it worked great. It was really one day, from my perception, of course, I wasn't the one in the lab, 16 hours a day, my graduate students working really hard, but I go away and come back and say, wow, today is making amazing progress. You've got it, there's the gate. And then within a fairly short period of time, from my perspective, we were walking and running around outside. And there wasn't there's no perception, of course, but it was able to handle all kinds of terrain and handle obstacles and transition, walking to running and everything else. So it sort of captured those core physics, right? That was really the valuable, important piece of that. But when it breaks all the time, you can only walk and run, it can't even stand, etc. So the next step then with Cassie, there was a big problem with Atreus. And my Andy Abadi was working with me, still is, pointed at the antagonistic work. And a lot of people in robotics have sort of seen this. Back in the 80s, they've seen it, but it hasn't really been looked at in close detail, and Andy did. The problem is that one of these motors is always acting as a brake and doing negative work on the system, and the other motor has to overcome that negative work and do the work on the world. And that's just a function of that leg configuration. When you're applying some force through some trajectory, you're getting that effect all the time. So the Cassie leg configuration, and to this date, the digit leg configuration, is basically aiming to capture the same dynamics and the same capabilities of the Atreus leg, while eliminating that antagonistic work problem. And the fact that it ended up looking like a bird is pretty cool, but we didn't set out to make a leg that looks like a bird. We set out to make a leg that behaves like a certain physics model, so we can capture the foundations of the physics and then start to make it practical and useful on the machine. I think that's cool. And a lot of times I see that in robotics. When you find a solution, maybe it solves three different things at once, and then it ends up looking a lot like an animal, you're kind of going in the right direction. So the next stage then from Cassie, we say, okay, obviously the plan always was we need to add some, manipulators and other things to it, but we were actually starting with kind of still on the mobility problem. When the robot's running, one of the main problems is that the yaw control it is very hard to deal with on a biped like this. You're swinging a leg and the robot would twist. And so we looked at, there's very little inertia in that body. It's like a little basketball. So we looked at how do you add, flywheels or gyros or a tail to the robot. And what we really want to do is rotate about the central axis. If you look at tails in animals, a lot of times that's for leaping, or bipedal animals like dinosaurs or lizards. They leap and then they want to reorient their pitch. But we want to control the yaw. And what we ultimately came down to is that a pair of bilaterally symmetrical tails is really the optimal solution. You want one on each side so that you can rotate around the center, and they can, not have that center of rotation be offset. Now, where do you put those? If we want to put those on Cassie down low, now the thing is so wide, it's not going to go through doorways. It's not going to be very useful. You want it to be narrow, and we need a bunch of inertia in that body to react against when the legs are swinging and you're trying to maneuver yourself. So we can make the body long or we can make it tall. And it's just, we tried everything, and this is the configuration that makes sense for mobility. Now, there's a very similar story going on with the foot design, but maybe I'll leave that for another time. Now, I talked about reduced order models, And everything is model based. But it's a question then of how do you build or how do you create that model? It does get more and more complicated for something that's this many degrees of freedom. But even for the mobility side on Cassie, I wanted to show this recent work from Oregon State, and Jeremy and Kevin are in the audience here in LA, have been doing this work. The thing that's really cool about reinforcement learning approaches is that it kind of gets into the corners of the dynamics. In other words, when we started out using spring mass models or linear inverted pendulum models or things like that, it's obviously not capturing the full range of what the hardware can do. But if you learn the system, you can basically learn into those little corners, and the robot sort of freed up. When it was walking with the reduced order models, my perception of it is fairly stilted and fairly limited in what we can do with it. But then with the learning policy, and these are black box policies, just running the single policy on the robot for the walking of the running gate, we ran a 5K across campus, used half the battery pack power to go full 5K. I think it was something like 43 minutes in that amount of time. It's not that fast, but not too shabby. We're also, been running 100K. We'll put that. All right, sorry, 100-meter dash, but we'll talk about that at a later date. All right. So the problem, of course, with reinforcement learning is I don't know how it works. The robot does some strange behavior and I'm not really sure why, and that's really frustrating. The other problem with reinforcement learning is, these are black boxes. We have the running controller. We can also have a look on YouTube. We'll see our video of it going up and down stairs completely blind. That's amazing that it can do that. It doesn't know if the next step is a step up or a step down, and yet this biped can just go up and down stairways. But now, how do you say unload a tractor trailer and integrate perception and planning and everything else with the learning policy? Well, that's where control hierarchies come into play, but it's still very much an open problem, an open question, and we're working on it. So I talked about arms helping the mobility, which they do. But also important is to note that legs are a part of the manipulation. And this is my strongest argument for why it's useful to have legs when you're trying to get around in human spaces and human environments. You can pick things up off the floor, lift them up, and set them up on a top shelf. And it's a very compact form factor. This is a very small robot for the range and the reach, the workspace that it has. And I don't think you can do that, or I'll just say, I think this is a very good solution to achieve that. I wouldn't say that it is optimal or the best solution, or that there aren't other solutions that might work. This is a very good one. Once you can walk around, once you can plan your space, and once you do have those low-level dynamics, the efficiency is very good. More than half the power draw of this robot is the computing on board. It's actually not the actuators and anything else. So there's quite a bit of room for improvement. But I don't think there's a whole lot of drawbacks once you know how to do it. That's the hard part, right? One other thing I wanted to mention on the previous slide, if I can get there. Why was this successful, right? So this was, to my knowledge, the first time anybody had balanced a biped and done real dynamics with reinforcement learning. We didn't really innovate a lot on the actual learning side. What we did was we took all of the knowledge about how does leg locomotion work, and we're very careful and intentional about how we created the cost functions and how we designed the problem so that the learning algorithms could only find that one solution. So we're not relearning physics, we're not relearning the models of the robot, we're not relearning. We're trying to tell it as much as we can without our constraints. So that's just one thing I want to do. Okay. And then I'll just kind of finish up here to say, look, that the real usefulness builds on foundations. So, like I said, you can't just tell your foot to be in a certain location and position control it there, because the location to place your foot is a function of your balance. Like, where do you need to place your foot in order to not fall over? It's already an answer. And then where do you want to place your foot? If it's on a stairway or something like that, it's a different answer. And so you really have to be thinking ahead. I mean, it's just like when you're walking up to a staircase, think about that, and you approach it, take a couple of short steps before you go. So you have to plan through that foundation of the dynamics first in order to stay on track. And then the perception of this is all, it's very similar to how any robot is going to do perception. We've got the depth sensor, the stereo cameras for the depth sensors and detecting surface planes. We don't really care if that's accurate to within an inch or two. It could be off because we've got a lot of robustness in that foundation. The LiDAR that tells us the map of the space and where people might be, and that's the same as any other robot we might see. And it's just kind of layering all of that up on top and integrating it all. So I will wrap up there, and I wanted to make sure intentionally that I left some time for questions and can flip back between slides because there are a couple of different topics for conversation. Walk the robot around. Yeah, thank you. Question. I don't know if anybody's had a chance to come interact with it, but the robot, the sort of compliance and the force that you apply on the world, that's a really important feature for how it's able to interact with the environment. You think of physical interaction, the whole point of that is it's a two-way transition of information, two-way information transfer. So you may not know you're going to impact something, and you have to have engineered your dynamics. When it does make that contact, it's going to be a good interaction. So engineering your dynamics is what it's all about. Question?
Thank you. Amazing. The question is related to the question of the previous talk. So when it takes the payload, do you know in advance the weight of the payload, or do you estimate it online?
It depends. So we've done a bunch, it's very robust to, all the kinds of things you would do. We've done like holding a tote, and our engineer Taylor dumps a whole bunch of water bottles into the box, and it's fine. The robot can handle that. And yes, estimate how much is the deflection, how much weight is in that box. Typically, it's going to be better off if you have some estimate of what the weight is going to be. So when we're going to be, unloading trailers and things, what we're going to want is some information and estimate of what we're about to pick up. But just like when you pick up something, you pick up a glass and you think it's full of water and it's empty, you kind of overestimate it. This is going to do the same exact thing because it is about applying forces on the world. It's not a CNC machine moving up the trajectory.
So you give him a trial basically, and then you adapt online.
Yeah. Anybody else? Okay.
In the Cassie, you guys have only 1 meter freedom for ankle. Now you guys have two. How important is that?
Okay, I'll tell the story about feet a little bit. So when you're walking on ice skates, right? You have, even before that, with Atreus, we had nubs on the feet because you don't need feet to walk spots. Atreus walked and ran very well as a spring mass model with no feet. The problem is it would twist uncontrollably, and then it would be sidestepping because its velocity and its orientation would be in some way. So we had to add just feet that were completely passively actuated just to keep it mostly going in the right direction. With Cassie, we added actuators there so they could stand because unless you actuate your ankle, it's just a stiff overfall. With both feet on the ground, you can stand. And so the first versions of Digit were like that. We're trying, everything we do is to keep it as simple as possible. Only add a feature when we understand exactly how it works, exactly why it's necessary. But in the sorts of scenarios where you are constrained in your footstep location, and like I said, that kind of contradicts where you need to place your feet for balance. And the primary method of control is where you place your foot. But when we're doing something like going up and down stairs, it takes a while to get that next foot down. You're moving a little bit slowly, and that whole time you're falling in one direction or the other. You're walking on an ice skate. And so what we found is you basically have to run up steps if you're going to have, or stepping stones if that's what you're going to do. And you need a little bit of secondary control there to control your center of pressure a little, so that in the middle of stances, in between foot placement, primary control, you've got also a little bit of control for the side-to-side angle. Now, what's happening though is that we've got these physical springs still up high in the leg, and those have been very, very important for, say, Cassie running a 5K. You need that spring for that impact. But what we're doing is we're moving that impact handling down to, because we have to put that mass and that inertia there for the ankle control. So now we've got to really get sophisticated with how our foot contact works. Turns out that's a really complicated problem. It's a lot more complicated than I thought it was. And so we've done some quite a bit of work on that. We know how to do that, and handling that well, eliminates those impact forces, reduces the noise, and a lot of that. We had a pogo stick hopping up and down, and dead silent hopping up and down. Yeah.
You started kind of getting into my question about the springs.
Yeah.
I've had the opportunity to work with Cassie, and I've kind of seen how Cassie too, the spring stiffness increased in other environments, especially. I'm just wondering kind of where you see this is one of the robots that uses springs, kind of where you see the trajectory of the spring. You kind of started getting into comments a little bit.
Okay, so the question is, what about the springs?
Yeah.
Now in Atreus, we made a spring mass model, had big giant physical springs, and we proved beyond any doubt that yes, spring mass locomotion is real, does stabilize well, can do walking and running. But you can only do walking. We designed the passive dynamics into them. And I know, like, for a long time now, ever since back in the day, Boston Dynamics has taken a very different approach, which is put these very high bandwidth, very powerful hydraulic actuators on there and do all the dynamics in software. And I really feel like the answer is going to be in the middle. And that's what we see as we get a better understanding of the sophistication of models. No longer just a simple spring mass model. There's a lot more to it. We're trying to get around the world. And you break down what are the important pieces. So it's the impact handling, which has to do with the inertia of the limbs, the reflective inertia of all your joints, the transmissions, and everything else. You need to handle that. And you also need to be able to play the right dynamics in the middle of stance. And so you can do that if you have very transparent transmissions. You can really control the forces if you want to apply on the ground, and do that then through software. But we found with the electric actuators that inertia is always going to be there. And so that impact handling really has to be done in some passive dynamics. But I think that also all the controls people bitch and moan and complain constantly about springs in systems, right? The second order dynamics cause oscillations. We know that it's possible to use springs, and we know that in the limit, when we get things really refined to high performance, high efficiency, we will have springs in systems almost certainly, because you see it in biological systems and you know that it can be controlled. Physics is true whether it's a robot or an animal, it'll work. Okay, but for right now, we're not going to be running and jumping and doing marathons, with digits. We're going to be walking around, human speed, human spaces, et cetera. I think we can handle the impacts with the way we're designing the feet. And I think we can be very careful about how we do the force transmission without having to measure spring deflection, but other ways to measure the forces through the rest of the leg, and then make it a lot easier on the control spokes for whole body manipulation, which is really a big part of the business. I do think for high speed running and things like that, it's still Thank you. We're out of time.
Yes,
I'll hang
there's
on
one
to
question
some-
from the internet, from Zoom first, and then maybe we can do that later on offline. Hold on, so I save that. So actually, Majid Karim is asking, what do you think of scaling the RF controller from Cassie to digit? And I was wondering, this is running a model-based controller, not an RF controller, right?
All of the above.
Okay.
So I'm not dogmatic about the tools. What I care about is, can we engineer the dynamics of the system? Can you engineer the dynamics of the system using passive dynamics, of course, using optimization tools, using some sort of reduced order models, using reinforcement learning? All of these tools have their application in different spots. And just an engineer, I would say that the software and the control side of the engineered system is more complex, more sophisticated, and than the hardware aspects of the design. Although the hardware aspects have to be right in order to enable the software to even function. A saying that I've heard that I like is a rock can't fly, no matter what software you write for it. The hardware really has to be done well, but our software team is bigger than our hardware team is growing faster. And I think that's Did I ask the question?
No, so Digit has an RF controller now, or is that a model-based controller right now?
All of the above. So
So-
there are pieces of RL in the robot, doing throughout the control hierarchy, doing some of the really hard to model and weird things. And then there's also a model-based controller. So, yeah. Okay, well, thank you.